Okay, let's dive right into this explainer. We're going to completely unravel the logic of Visual Basic programming today so that writing clean, effective code becomes entirely second nature to you. We are looking specifically at the common conceptual traps that consistently trip up students year after year. Instead of just memorizing syntax, we're going to build a fundamental understanding of how the code actually operates, ensuring you can navigate any scenario without just falling back on guesswork. So picture this. The clock is ticking down, you sit at your desk, the paper is flipped over, and boom, you are immediately faced with a programming scenario that seems incredibly straightforward, right? Well, watch out, because it's actually a clever trap that catches out the vast majority of candidates. Dealing with these scenarios isn't just a matter of knowing the code by heart, it's about keeping a cool head and understanding exactly how to structure and justify your logic when the pressure is really on. When you fundamentally misunderstand assignment logic, your entire program just breaks down. It's like a jammed gear in a massive, complex machine. You might look at a basic piece of code, like an if statement checking a grade, and think, yeah, that makes intuitive sense. But if it lacks the proper syntax, say missing the quotation marks needed for string data, or just misusing assignment logic entirely, well, the mechanism of your code simply refuses to turn. This fundamental misunderstanding of how a computer processes instructions is exactly how easy marks slip away. To keep that engine running smoothly and make absolutely sure you're answering these exam questions comprehensively, you need a bulletproof framework. It's a four-step process. First, you've always got to state the core concept clearly. Second, extract your evidence or data directly from the scenario they gave you. Third, apply scientific reasoning to show exactly how and why the code works. And finally, package the whole shebang using precise, examiner-friendly wording. Relying on the structural engine ensures you provide thorough, high-quality answers every single time. Now, what's really fascinating here is that examiners actually use a highly specific, almost secret language designed to test your precision. Command words like state, explain, and evaluate are basically cheat codes for your response. If a prompt says state, they just want one distinct, concise, technical point. If it asks you to explain, you've got to dive into the underlying mechanism, give them the why and the how. And for evaluate, your answer absolutely must tie directly back to the specific real-world scenario. Before we try fixing any broken code, we really have to nail down the core concept of selection. Basically, this is how a program branches down different pathways of logic. Think of it kind of like a teacher grading an exam. The teacher looks at your specific score, compares it to the established grade boundaries, and then makes a decision on what letter grade you get. Selection lets a computer program do this exact same thing, automatically navigating complex branching paths based on specific criteria. You can see this perfectly in the mechanical flow of something like an automatic door. It decides whether to open based on a sensor. And the sheer speed of this logic is mind-blowing. Literally in the first millisecond, the system receives the input data. By millisecond 2, the code is evaluating the criteria, asking, hey, is a person standing there? And by the third millisecond, it instantly routes execution down path A to slide the doors wide open, or path B to keep them locked tight. Now, finding the right logic in a really complex programming scenario is a bit like finding the golden puzzle piece in a massive pile of interlocking gears. Once you spot it, everything else just clicks into place. But to spot that crucial piece of logic, you need to deeply understand the system's underlying framework. Understanding logic isn't about blind memorization, you know? It's about seeing the matrix of the underlying rules and applying them with absolute confidence. It's exactly like placing distinct, colored flags along a measuring ruler. Computers make decisions by evaluating variables against strict, predefined boundaries. So if your program needs to handle an entire spectrum of grades, like A, B, C, and D, it's going to need a lot more of those criteria flags to process everything correctly. The system evaluates the input, scans along the ruler, and triggers an action the very moment a specific mathematical boundary is crossed. When you just try to jam variables and operators together without any real care, you end up with a chaotic, broken mess of blocks that simply won't stand on their own. But when you structure your logic carefully, say evaluating a numeric mark with a greater than or equal to operator and deliberately assigning the correct string variable, you build a structurally sound, highly stable foundation. Properly stacked logic behaves predictably. Jumbled syntax, it just collapses the moment it's executed. To actually build those solid structures, you need to fluently combine variables with mathematical and logical operators. You'll calculate totals using arithmetic, and then deploy logical operators like and, or, and not to check complex conditions. And hey, if your program is facing tons of different paths, like a massive restaurant menu system, using a giant chain of if statements is going to get incredibly tedious. That's exactly where case statements step in, acting as a super efficient switchboard to route your data instantly. So here is an absolutely crucial distinction you must master: the difference between validation and verification. Don't mix these up. Validation acts as a protective shield for your program. It guards against bad data by checking if a user typed in a sensible number, like making sure an exam mark is actually between 0 and 100. Verification, on the other hand, is more like a scale. It weighs two inputs against each other to ensure they match exactly, like when a website asks you to type a new password twice. All right, once your code is structured, you have to actually prove it works mathematically. You do this using trace tables, which are basically grids to track how variables change line by line, and perfectly selected test data. You've got normal data, which is your everyday expected input. Abnormal data should bounce right off your validation shield. Extreme data pushes the very outer limits of what's acceptable. And boundary data? That sits right on the absolute mathematical edge, like meticulously testing exactly 69 and 70 to ensure a grade boundary behaves perfectly. So I want you to pause for a second and ask yourself, if a complex system suddenly fails, where does the logical arrow usually hide? Is it buried somewhere in the string assignments? Is it a misused logical operator? Or maybe the boundaries themselves just aren't mathematically sound? When you train yourself to mentally isolate the different components of your code, spotting the error transforms from a stressful guessing game into a really methodical process of elimination. Let's put this into practice. Say your coding scenario revolves around an automated smart greenhouse. A vague, low-band answer simply claims that the system checks a number. Not great. But a top-band, high-quality answer, it uses specific nouns derived straight from the prompt. It'll state that the program validates the temperature sensor input against the extreme data bounds of the greenhouse environment. Grounding your programming logic strictly within the context of the given scenario is the ultimate key to maximizing your marks. By combining flawless Visual Basic syntax with that rigorous concept, evidence, and reasoning framework we talked about, you elevate your code from average to exceptional. Honestly, it all comes down to mastering three distinct types of precision. You need structural precision in your code, vocabulary precision in your terminology, and mathematical precision in your testing data. When those three elements align perfectly, your program will execute exactly as intended, netting you that full 100% top band score. And mastering these concepts isn't just about surviving a single mock exam or passing a one-off assignment. It's an ongoing process of equipping yourself with the right intellectual frameworks. Oh, and to guarantee your success, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. The more you immerse yourself in the logic of variables, operators, and selection structures, the more natural computational thinking becomes. You have officially unraveled the logic of the assignment trap and learned exactly how to build and test flawless selection statements. But this begs a much larger, even more fascinating question. Once you actually have the ability to write perfect individual lines of code, how do you step back and evaluate the structural integrity of an entire interconnected systems design? That broader perspective is the ultimate test of a programmer. So, what does your system look like from 1,000 feet up?